Something remarkable is unfolding in astronomy right now, and most people have no sense of just how significant it truly is. The James Webb Space Telescope is no longer merely validating ideas we already suspected. It is actively pushing past the boundaries of what we believed was possible. In an astonishingly short period, Webb has revealed planets that should not exist, atmospheres that should not endure, galaxies that should not yet have formed, and chemical signatures that drift uncomfortably close to the question of life beyond Earth. And no, this is not about K2-18b. What Webb is observing runs far deeper than any single world. Discovery by discovery, piece by piece, a pattern is taking shape. And that pattern suggests a universe far stranger, far more energetic, and far more inventive than our models ever permitted. Tonight, we will trace these findings step by step, because by the end of this story, you may realize that what once seemed unimaginable is no longer theoretical. It is already being observed. One of the earliest fractures in our understanding comes from a planet that makes little sense on paper. TOI 4507b is a gas giant roughly comparable in size to Jupiter. Yet its density is astonishingly low, far lower than expected for a planet of that scale. It is swollen, inflated, and unnaturally light, like a cosmic balloon that should have collapsed long ago. But what truly unsettles astronomers is not its size. It is its orbit. TOI 4507b travels around its star at an inclination approaching 90 degrees, meaning its orbit is nearly perpendicular to the star's rotation. Configurations like this do not arise gently. They point to a violent history involving extreme gravitational encounters or catastrophic orbital migration. And yet, the planet sits too far from its star for stellar heating to explain its bloated state. The James Webb Space Telescope is now probing its atmosphere in detail, attempting to determine what could possibly keep such a massive world so inexplicably light. Already, this single planet is forcing scientists to admit that something fundamental about planetary evolution is missing from our equations. As startling as strange planets are, Webb's discoveries extend even further. When it turned its gaze toward the early universe, it uncovered something even more troubling. Fully formed, actively feeding supermassive black holes appearing just 500 to 570 million years after the Big Bang. Objects within galaxies such as Sutras LRD, Z9, and GN, Z11 LRD8 carry masses hundreds of millions of times greater than our Sun. According to standard cosmology, there simply was not enough time for black holes to grow so large through conventional processes. These findings imply that black holes may form directly from the collapse of enormous gas clouds, bypassing the slow, incremental growth we once thought unavoidable. In other words, Webb is showing us that the universe learned how to build giants almost immediately. And if that is true, then much of what we thought we understood about cosmic evolution must be rewritten. Closer to home, Webb's revelations continue with worlds so extreme they sound almost fictional. Consider WASP-18b, an ultra-hot gas giant orbiting so near its star that its atmosphere reaches temperatures where water vaporizes instantly. Using advanced spectroscopy during planetary eclipses, Webb accomplished something never achieved before, a three-dimensional map of an exoplanet's atmosphere. What emerged was astonishing. Supersonic winds tearing across the planet, redistributing heat from the blistering day side to the night side, creating one of the most complex atmospheric systems ever observed. This is more than a scientific curiosity. It marks the beginning of a new era where alien atmospheres can be modeled in detail rather than imagined. And Webb did not stop there. It also detected a dense atmosphere around TOI 561b, a super-Earth orbiting extremely close to its star. Previous models predicted that such a planet should have lost its atmosphere long ago. Yet it has not. That single observation forces scientists to rethink just how resilient planetary atmospheres can be, even in environments once assumed to be completely hostile. Perhaps the most disturbing discoveries come from Webb's observations of the early universe itself. The telescope has identified a spiral galaxy already mature and well-structured just 100 million years after the Big Bang. This should not be possible. Galaxies are expected to take far longer to organize into such shapes. Either the universe began earlier than we believe, or there exists an unknown mechanism that accelerates cosmic structure formation dramatically. Then came the discovery of the oldest known supernova associated with a gamma-ray burst, detonating only 730 million years after the Big Bang. That explosion scattered the first heavy elements into space, elements essential for planets, chemistry, and eventually life. Webb is not merely showing us distant objects. It is revealing that the universe became complex far faster than we ever imagined. That realization sets the stage for something even more unsettling. As Webb pushed deeper into hostile environments, it began identifying planets that should not exist in their current form, worlds orbiting neutron stars and pulsars, remnants once thought completely sterilizing. Webb, alongside complementary observatories, has confirmed planets that somehow survived the supernova explosions that created those remnants. These worlds endured radiation capable of shredding atoms, shock waves that should have expelled nearby material, and gravitational chaos that typically tears planetary systems apart. And yet, they remain. Even more disturbing, some appear to retain atmospheres or surface materials suggesting long-term stability. This forces astronomers to confront an uncomfortable truth. Planetary resilience is far greater than we ever allowed for. If planets can survive the death of a star, then the boundary between habitable and uninhabitable becomes far more blurred than our models suggested. Among Webb's most disruptive contributions is its growing list of exoplanets that maintain thick atmospheres under conditions where atmospheric loss should be unavoidable. Super-Earths orbiting perilously close to their stars, bathed in intense radiation, were expected to be stripped down to bare rock. Instead, Webb has detected atmospheres rich in heavy molecules, hinting at powerful retention mechanisms or continuous replenishment from planetary interiors. This suggests that planets are not passive victims of their stars, but active systems capable of sustaining equilibrium far longer than anticipated. Volcanism, magnetic fields, and deep reservoirs of gas may play far greater roles in planetary survival than previously believed. The implication is staggering. Worlds once dismissed as dead may still host dynamic, evolving environments beneath their hostile surfaces. Webb's spectroscopic power has also revealed chemical combinations in exoplanet atmospheres that should not coexist for long periods. Methane alongside carbon dioxide, sulfur compounds persisting under extreme heat, and water vapor surviving intense stellar radiation all point toward active chemical cycles rather than static compositions. In equilibrium, these molecules should rapidly destroy or transform one another. Their persistence implies constant replenishment or regulation, processes that keep atmospheres chemically out of balance. This matters because chemical disequilibrium is one of the strongest indicators of dynamic systems. It does not mean life, but it does mean activity. It means planets that are not chemically frozen, but constantly evolving, reacting, and reshaping themselves in ways that challenge long-standing assumptions. Taken together, these discoveries erode the traditional notion of the habitable zone. For decades, habitability was defined as a narrow band around a star where liquid water could exist on a planet's surface. Webb is demonstrating that this framework is far too limited. Worlds outside this zone retain atmospheres. Worlds inside it may be far more extreme than expected. And worlds once deemed completely hostile may still support complex chemistry. Habitability, it seems, may not be a location but a spectrum, a sliding scale where chemistry, energy, and time interact in ways we are only beginning to grasp. If that is true, then the number of potentially interesting worlds in our galaxy does not increase modestly. It explodes. As Webb continued dissecting exoplanet atmospheres molecule by molecule, scientists noticed something that quietly triggered alarm bells. Certain planets displayed chemical combinations that should not persist unless something was actively maintaining them. Under stable conditions, gases like methane and carbon dioxide react and disappear over relatively short timescales. Yet Webb kept finding them together in atmospheres exposed to intense radiation and stellar winds. This is not a statistical anomaly. It is chemical disequilibrium, a state where inputs and outputs are continuously balanced by active processes. Importantly, this does not automatically imply life. Volcanism, photochemistry, and deep interior reactions can also drive such imbalances. But the realization is unavoidable. These planets are not chemically dead. They are dynamic systems, constantly processing energy and matter in ways that defy decades of assumptions. Even more unsettling is where some of this activity appears to originate. Several exoplanets observed by Webb receive far less stellar energy than would normally be required to sustain such complex atmospheric behavior. In other words, the star alone cannot explain what we are seeing. This forces scientists to elevate internal energy sources, tidal heating, radioactive decay, deep mantle chemistry, from secondary considerations to central roles. Entire planets may be running on internal engines, releasing heat and material over billions of years. This dramatically expands the number of worlds that could remain active long after their stars begin to fade. It also suggests that planetary evolution may be far more independent of stellar evolution than our models ever allowed. At this point, a dangerous temptation arises, labeling these signals as evidence of life. And this is where the scientific community has exercised extreme caution. Webb has not detected life. What it has detected are conditions that resemble environments where life could operate, without proving that it does. This distinction is critical. False positives have haunted astronomy before, from Martian canals to misinterpreted spectral lines. Today, scientists face a paradox. The data is richer than ever, but so is the risk of overinterpretation. Every potential biosignature must be tested against countless non-biological explanations. And yet, the uncomfortable truth remains. If life does exist elsewhere, this is exactly what the earliest signs would look like: subtle, ambiguous, chemically suggestive, but never definitive on their own. By now, one conclusion is impossible to ignore. The universe does not respect the neat categories we built for it. Planets are not simply dead or alive, habitable or hostile. Atmospheres are not either stable or gone. Galaxies do not always form slowly. Black holes do not always grow patiently. And chemistry does not wait for ideal conditions. James Webb is revealing a universe that is opportunistic, fast, and astonishingly efficient at generating complexity wherever energy and time intersect. This does not mean the cosmos is filled with life, but it does mean that the processes leading toward life are far more common than we ever dared to assume. The most unsettling realization is not any single discovery, but the pattern that emerges when all of them are viewed together. Webb is not finding isolated anomalies. It is finding the same kinds of surprises repeating across different star systems, planetary types, and environments. Hot worlds and cold ones. Gas giants and super-Earths. Planets around calm stars and violent ones. All showing signs of unexpected complexity. Atmospheres that refuse to collapse. Chemistry that resists equilibrium. Internal energy sources that keep planets active long after they should have gone silent. Randomness does not repeat this consistently. Patterns imply underlying rules, and those rules are not the ones we have relied on for decades. Webb is quietly telling us that complexity is not an exception in the universe. It is the default outcome whenever matter, energy, and time are given room to interact. As these patterns sharpened, the scientific community did something rare. Instead of rushing toward dramatic claims, it slowed down, carefully and deliberately, because everyone understands what is at stake. The chemical signatures Webb is detecting sit uncomfortably close to what we would expect from biological processes. But expectation is not evidence. Methane alongside carbon dioxide. Long-lived disequilibrium. Internal energy driving atmospheric renewal. All of this can arise from non-biological mechanisms under the right conditions. And yet, this is exactly why the moment feels so tense. For the first time, astronomy is brushing against a boundary where the data is no longer comfortably abstract. It is suggestive, ambiguous, teasing. Webb is not shouting life. It is whispering something far more unsettling. The universe keeps building environments where life would not be surprising. That is a profoundly different statement. For decades, the search for life beyond Earth followed a narrow path. Earth-like planets around sun-like stars at just the right distance. James Webb has shattered that strategy. What it reveals instead is a universe where potential spreads across a vast spectrum of worlds. Planets too hot still sustain chemistry. Planets too cold still generate energy. Planets that should be stripped bare somehow retain thick atmospheres. The implication is staggering. The question is no longer how many Earths exist, but how many pathways toward complexity are available. And once that question is asked, the numbers stop being comforting. They grow enormous. Taken together, these discoveries give the word unimaginable a precise meaning. It does not refer to aliens or civilizations or definitive proof of life. It means the universe operates with a level of creative efficiency we never accounted for. Webb is showing us that planets do not require ideal conditions to become interesting, that chemistry does not need gentle environments to grow complex, and that time does not require billions of calm years to produce structure. The truly unimaginable realization is not that life may exist elsewhere. It is that the universe appears almost compelled to try again and again, in places we dismissed, under conditions we ruled out, using mechanisms we are only beginning to understand. At this point, the data leaves us with one unavoidable conclusion. We are no longer asking whether the universe can produce complexity. We are watching it do so in real time across the galaxy. So where does this leave us? After tracing Webb's discoveries across planets, atmospheres, galaxies, and chemical systems that refuse to behave as expected, one truth becomes impossible to deny. The universe is not cautious. It does not wait for perfect conditions. It does not confine complexity to narrow zones or rare worlds. It experiments everywhere, relentlessly. What Webb has uncovered is not a single shocking result, but a new pattern, one that forces us to rethink how reality itself operates. For years, we framed our search around a simple question: is there life out there? James Webb is quietly suggesting that this question may have been too small. What we see instead is a universe filled with active chemistry, persistent energy sources, resilient atmospheres, and worlds that refuse to become inert. Even when conditions appear hostile, complexity finds a way to survive, adapt, and continue evolving. That does not mean life is everywhere, but it does mean the road toward life is far wider, far more forgiving, and far more common than we ever allowed ourselves to believe. And that is why this moment feels so unsettling. Because once you accept what Webb is showing us, the silence of the universe no longer feels empty. It feels patient. The question is no longer whether the universe is capable of producing extraordinary outcomes. The question is how many we have already missed simply because we were looking the wrong way. James Webb has not given us all the answers. What it has done is far more powerful. It has forced us to acknowledge that the unimaginable is not a future possibility. It is already happening. As Webb continues to observe and future missions build on its legacy, one thing is certain. The universe we thought we understood is gone. In its place stands something far more dynamic, far more creative, and far more alive with potential than we ever dared to imagine. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.